begin with, let me kind of show you what's going on this basic problem here. And I took this one out of the book. I thought this was kind of an interesting problem for this section. So what you have is you've got some sort of a building that's fixed at 150 meters, and then you got a ship, and that ship is kind of moving towards the building. So a couple of things I want you to think about on this. The idea is, as that ship moves towards the building and away from it, well, two things change, okay? A couple of things change. Now, let's just think about this for a minute. So, as the boat goes out, what happens to that angle? It's smaller, right? Now, it'll never go to zero, but if it went far enough out, it would kind of go to zero, wouldn't it? Okay? How about if you're real close? What kind of angle do you think that is? It's getting real big. It's getting close to what? 90 degrees, actually. Right. Okay? And then this is just the distance, how far that is. So what's happening is that if that angle's changing as the boat changes its direction, but we're going to look at what that rate is. Okay? So that rate is going to change also. So what we're going to kind of do is start like right there when we're just looking straight up at like a 90-degree angle, and then that angle is going to change and eventually get to zero, okay, theoretically anyway. So what we'll do is we'll go ahead and get this set up. Now what we're going to do is we have a right triangle. So there's two ways I could start this. I really have two choices. I could say tangent of theta, okay, and that would be opposite over adjacent, like you learned in trig, okay, would be 150 over x. That would be one way to do it. The other way to look at it would be cotangent of theta, and then that would just be the opposite. That would be x over 150, like that then. Okay? Now, it doesn't really matter. You'll get the same result either way, but what I'm going to do is I'm going to go this way, and the reason I'm going to go that way is because if I solve for x, then I just have x equals 150 cotangent theta. That's kind of my thinking on that. It just makes it a little simpler. You don't have any fractions or anything. So that's the way we're going to start it. So you can start by writing down cotangent theta equals x over 150. And what we're going to do on this is you're supposed to find d theta over dx. You're finding the rate of change. I got it fixed. Okay. I just played with it, pressed buttons, and it came on eventually. So, okay. Thank you. Okay. All right. So what we're going to do next is we're going to write theta. Now, this is something you kind of get from trig. You got to remember how to do that. How would you write theta? What theta is equal to? Has something to do with inverse cotangent. So what would it be? Exactly. It'd be inverse cotangent of x over 150. So what we're doing in this section is we're talking about derivatives of inverse trig functions. So it's an application of that basically. All right. So that's what the idea is. If you do the inverse cotangent of x over 150, then you get the angle. Okay. So what we're going to do is we're going to just differentiate. So we got to do this implicitly. The problem says, I believe the directions say that you want to find d theta over dx. So what we're going to do is we're going to do d dx of both sides, like that. So I'm going to go ahead and write that out, and we're going to do this implicitly, and then that'll give us what we're looking for, and then we'll look at this graphically to try to make sense of this, okay? All right, so really what you do here is you just say that's d theta over dx, okay? You're really doing the derivative of theta is 1, variables don't match, we're multiplying it by d theta over dx, okay? And then it goes like this. What we learned is the cotangent, remember, was negative 1 over 1 plus x squared. That's what the derivative of a cotangent is. Okay, like if you're doing the derivative of cotangent of y or something like that. That's the formula that you learned, okay? So what we're going to do is we're just going to apply that formula. So we're going to do this like this. We're going to say negative 1 over 1 plus. Now, instead of putting an x there, you put this thing there. And then you got to apply the chain rule on this. So you want to put in x over 150 to the second, like this. Okay, then what you have to do from there is you have to multiply by the derivative of x over 150. Okay, so that's how that goes. I'm applying the rule we talked about last time. All right, everybody following okay so far? Okay, a little basic trig. Then we're doing a derivative formula here. Okay, we need to clean this up. It looks kind of like a mess there. So I'm going to write this down as negative 1 over 1. I'm going to go ahead and write this just as x to the second. And I'm going to write that as 150 to the second. You could multiply that out on your calculator if you want to. It doesn't matter. Okay, now what's the derivative of x over 150? Not quotient. You could do quotient rule, but you don't have to. There you go, 1 over 150. It'll work if you do the quotient rule. But see what this really is it's 1 over 150x, right? So it's the number in front. Okay, so that derivative is going to be times 1 over 150 like that. Okay, so there's our derivative, and we just need to go ahead and simplify it a little bit and see what we get on this then. So really all I'm going to do on this is I'm going to write this like this. I'm really multiplying the numerator by this. This is going to kind of go through the numerator like that. So that's going to be negative 1 over 150 all over 1 plus x squared over 150 squared. Okay, like that. So then I'm going to get rid of that complex fraction. Okay, then that'll get me in a form that I like that's pretty simple. Okay. All right, so if I want to get rid of 150 squared, well, what do? You multiply by 150 squared, right? So what I'm going to do is multiply the bottom by 150 squared, and then I have no choice but to do the same to the top. Okay, that's a complex fraction. Your job is to get rid of the fractions. Okay, so if we do this now, what's that numerator going to be? 150, right? One of them cancels out because you got a square there. So that's negative 150. And then in the bottom, you're doing a distributive property. So 1 times 150 squared, I just write it as 150 squared. And then when I multiply these out, that cancels, leaving you x squared. So what our conclusion is d theta over dx, that's the rate of change of that angle as x is moving, is represented by negative 150 over 150 squared plus x squared. And then I want to look at this graphically to kind of try to make sense of this. You guys follow the algebra and calculus I did on that, okay? Okay. Now you could have done that problem with a tangent. You still would have got the same answer. I think it's a little easier to go with the cotangent on this, but you ultimately still get the same place. Okay, so what we're going to do next is we're going to graph this. So I want you to get your calculator out, and there's a couple of things that I want you to do here. First of all, what I want to do is do a graph of the original function. So I want to kind of go back to here, and I want to graph this. I really want to do 2 graphs. Okay, so let's do like y equals inverse cotangent of x over 150. I want to get the graph of the function, then I want to get the graph of the derivative. Okay, now when you do this now, you don't have an inverse cotangent button. So what you actually have to do in your calculators, you have to put in y1, you have to put in inverse tangent, then you got to do that backwards. Okay, so that's how you actually have to do an inverse cotangent in your calculator, is to change it into an inverse tangent because you have that button. Okay, so you want to put this in like this then. Just put in, you want to make sure that you're in radian mode, because we're going to deal with radians, okay? And I'll kind of give you a viewing window, so make sure that you're in radians, and you want to get that in. Okay, now the window, I'm going to show you a window I want you to use. I'll slide this over here so you can refer to that. So I want you to put in that viewing window, and this right here is pi, and then this is pi over 2. So the reason I'm doing that is because we predicted, if you looked at this, we kind of thought 90 degrees is the biggest angle you're going to get. And I just decided I'll make it go up to pi. That's the y-axis. The y-axis is representing what the angle theta is, and then x is representing the distance the boat is from that building. So if you get that put in, and then if you type graph, this is what you should come up with, okay? Like this. And what I want you to do is I'd like you to just make a real simple sketch of this. All you got to do is just label like pi over 2. That's good enough. Well, that's what pi over 2 is. And then that's 1,000 meters like that. That's kind of the key stuff. Okay, now what that is that's the function that's representing how the angle is changing as x changes. And before we do the derivative, let's see if this makes any sense to us. Makes good sense to me. Okay, the idea was, as you're real close to the building, what did we say the angle was? Real big, right? Real big. Like 90 degrees, okay? So if you're right by the building, you're looking straight up. So that's 90 degrees. Now, what did we say is happening as the boat goes away? It's getting smaller. See how that angle's getting smaller? And it's going to zero like we would expect it to. Does that make sense? Now, this is not realistic because the Earth curves, by the way. So if the Earth was flat, it'd be a little bit more, there's still some people who think the world's flat. There's a flat Earth society I've heard of. So anyway, that's kind of logical to me, all right? So that derivative, you would expect that derivative to be always negative, right? Okay, so what we're going to do next is we're going to graph the derivative and kind of take a look at what that looks like. Okay, does that make sense to you guys? The angle's changing. That's what that's representing. So the next thing I want you to do on your calculator is this. Okay, we're going to start over again. So just clear out that, and now we're going to put the derivative in. So the derivative is right here. We're going to put that in. So you want to put this in like this. You got negative 150 divided by, now you got to use parentheses, and then you want to have 150 squared, and then plus x to the second, and then close your parentheses like that. Okay, now we are going to have to change the window a little bit on this one too. So, because what this is going to do is it's going to give the rate of change. And you can tell that the rate of change is always negative. Everybody with me on that? Okay. And what it's happening is eventually it goes to zero, that rate of change. So the derivative, you're going to have a function that has all negative values going to zero, kind of like that. So let's do a window like this for this function, okay? So let's do, we can still do 0 to 1,000 because that's still x, but what we need to do is we need to change this around, and I kind of played with this a little bit on the calculator, so I'll show you what I want you to put here. I want you to put like negative 0.009. I had to play with this a little bit. And then 0.09. I'll explain to you in just a minute how I figured that out. And then we can maybe make a scale of, say, 0.001. See, these are rates of change, and you have actually pretty small rates of change, and those are in radians. Those are values of the rate of change in radians. Okay, so I'll slide that over there if you need to get that set up. Okay, now if you graph this, this should be what the graph of the derivative looks like, is like this. Okay, so I want to kind of look at a couple of things on this and see if this makes some sense to you then. I'm going to just slide this over here for now, and then I'll put the derivative here. Okay, so one thing that I would like you to do somewhere in your notes, just a simple graph, just real simple graph. Just do, you want to label that this is the graph of d theta over dx equals negative 150 over 150 squared plus x squared. That's 1,000. This is like negative 0.009, and that's all you really care about, like that. Okay, so let's see if this makes any sense to us. And there's, I think, one other thing we're supposed to do on this problem. So the idea is the rate that this is changing is the most there. That's when the rate's the most. Isn't that rate just kind of leveling off? Slope of the tangent line is leveling off. That's what this is showing. It's showing that the rate of change is the biggest there, and as you back away from the building, the angle is changing fastest. And then the further out you go, the angle keeps changing and it slows down. Does that make any sense? Okay? So see, that's what the calculus is representing, is it's representing rates. So like if you're going to get into engineering and physics and stuff like that, that's one of the big things we use calculus for, to represent rates, okay, and how things are changing. So that's the idea. So let's see, there was one other thing we wanted to do to finish this up then, and I think the problem said find the rate of change at x is equal to 500 meters. Okay, so let's do that, and we can do that on the calculator, but what we want to do, I'm kind of running out of room, so I'm going to write d theta over dx. We're going to evaluate that at 500 meters. So what we do is we just plug into our derivative, which is what I have highlighted in blue. So that's negative 150 over 150 squared plus 500. Okay, then you can take your calculator and just calculate that out. You'll get some decimals. You'll get some pretty small decimals, and you'll get a negative number. So let's see, negative 150, and then we're going to divide that by 150 squared, and then plus 500. Okay, then that should give us that rate of change. Okay, and let's see, I'll just round that off. I got that right? I think I do. Yeah, okay, so that looks like that's about...
Wait, now shouldn't it be 500 squared?
Oh, it is 5. Yeah, I thought there was something wrong on that. That didn't look right to me. Let me do that again. So I think that was a little different than that. It's not much different, though. So yeah, 150 squared was a part of the derivative, and then it was x squared. That's what I forgot. So 150 squared plus x squared. Up. Okay, so now let's see. If that about, yeah, that's what that is. So that's negative 5.5 times 10 to the negative 4. So I'm going to move the decimal back 1, 2, 3, 4 units to get negative 0.0005. And then that's really going to be radians per meter. Okay, that's what the rate of change is. It's the angle is changing by radians per meter. Every time a meter goes by, that's what that's saying then. Okay, and if you look at your graph, that's really what that's saying. So if you look at 500 right here, you have at 500 meters, then that rate of change is about negative 0.005 radians per meter. So that's what that's saying. That's what kind of helped me to come up with that viewing window as I calculated that out. Okay, does that make sense? Okay, that's kind of a good thing. We're kind of now going to be getting into the part of the class where we start looking at the applications of derivatives a lot. Okay, we kind of begin to get there, and then as you study higher levels, you get into that more and more and more. Okay.